Good afternoon. My name is Victor Kantor. I'm a chief data scientist with MTS. And now I will tell you whether we actually need supervised recommender systems. First, I'll tell you a few words about how we do supervised training of recommender systems. The key approaches are collaborative filtration and content-based recommender systems, as well as a hybrid approach. Speaking of collaborative filtration, we have the following. We have some users and objects. In this case, movies they watch on a certain streaming platform. And we have ratings that users give to movies they watched, or some other objects. Our task is to find an object that users have not rated yet and to try predict that rating to recommend the most relevant objects to users. Collaborative filtering only uses this spreadsheet with ratings to build recommendations. The simplest ways are probably closest neighbors method, would just find users that are closest to the one we're making recommendation for and just find an average for their ratings. You can also do it item-based instead of user-based. There are advanced methods of collaborative filtration, for example, matrix factoring. We try to build some vectors that would describe the interests of a user and the special features of a movie so that their multiplication would make it get a close thing to the ratings. It's a popular method, pretty well developed too. The vectors themselves are built in such a way that the error in prognosis is as small as possible using these two methods. There's another special feature. Feedback can be both explicit and implicit. Explicit feedback is when you have both positive and negative feedback, score, rating. Implicit feedback only shows one kind, positive or negative. In retail, for instance, we often get implicit feedback because we get positive feedback, meaning the client bought the goods, but we don't have any negative feedback because if a person doesn't like a certain good, they will never give a bad rating to something they don't buy. In this case, another popular method is used, which is ILS, implicit ALS. We give weights to both known and unknown numbers, and we give zeros to unknown ones because we're less confident about them. And we train the vectors with ALS. This is the classics of CF. On the other hand, we have content-based methods. This approach is predicting scores with a supervised model, machine learning, and we use parameters of users, objects, and their interaction. In this case, we're very likely to encounter content-based methods in retail. For example, we have lots of item parameters and user parameters that increase the accuracy of recommendations. Things like fill in the recommendation block with certain items usually imply that we want to profit off this block as much as possible. So it's profitable to show items where the confidence in the purchasing chance and price multiplication is maximum. We can get the prices of the catalog, but we have to predict the chances with a supervised model. The task for this model is the following. Classify threes: users, goods, time. The classes are purchased, not purchased. And for factors, we use the parameters of the user, the good, the time, like day of the week, season, etc., and their interaction. For example, combined factors like how often did the user visit the category of these goods in last week? We use both time, user, and good in this kind of factor. And you can also note that rating the chance for all goods in the catalog will take a lot of time. So the tradition is create a two-layer approach. first stage, we find candidates for recommendations using a weak model or heuristics, and then we rearrange them with a strong model. And now we actually give the chances. For candidates, we use popular goods, or popular in the category, or frequently seen, together with the ones that people already bought. Sometimes there are expert lists and recommendations from a weaker model, like matrix factored. Rearrange it with a more advanced model, supervised learning, like a gradient boosting, for instance. And of course, we need to generate negative examples too. Like I said, we often have implicit feedback. For negative examples, we can take random goods from uniform spread, which is a simple way. This way the model will learn to cache basic things. Or we can do it smarter. For example, make a sample from popular goods, or those that people never bought. Sometimes we use recommendations of the model. So to say, hard negatives that we could recommend but people didn't buy. And of course, it can be made hybrid, using CF model to sample candidates, or using CF forecasts during rearranging. These are the classics of supervised approaches to recommendations. Now, a few words about the quality of prognosis. Industrial experience shows that the approaches can be sorted the following way, from the least accurate to the most accurate. K closest numbers, matrix factoring. Then if you have parameters for users and objects, you can use the two-layer approach with the gradient boosting rearranging, and then the hybrid two-layer approach that can give an additional boost to the quality. It should also be noted that if you only have a matrix with ratings, the two-layer approach won't give you much boost, just because you don't have anything to build the model on. Now, to sum up about the practices in supervised rec system models, we can say that the two-layer approach is one of the strongest. Candidate selection, re-ranking. If we have enough data about users and objects, it's usually superior to matrix refactoring, and the two-layer approach can employ both CB and CF in one solution. Now let's discuss the pros and cons of such approaches based on supervised models. Pros first. We directly optimize the business metrics thanks to the choosing the targets connected to it. When we rate the chance of something, we earn more money. It's pretty simple and straightforward. We also get a higher quality on historical data. If you check the recall at K, precision at K, the most popular ranking and recommendation assessment systems. There are a lot of cons though. First of all, measuring the effect. High offline quality doesn't guarantee high online quality, and the closer the metrics is to the business, the harder to detect an effect. So, in fact, A/B tests are usually measuring proxy metrics to speed up the test and the solution making. But why don't we connect the target to proxy metrics? Why don't we check views instead of purchases? We will get more data as well. Well, you can do that, but you don't want to leave business metrics too much. And what should we optimize? The effect of recommendations is not that high in short term. Retail shows 2-3% of revenue increase, but that's a normal result. Long-term effects might be more important for us though. So choosing a target connected to revenue is not the best solution. So we have two ways. Way one, develop a more complicated approach to choosing the target, accounting for all the factors I've listed, all the metrics, all the data availability, etc. Way two is just forget about direct optimization of business metrics. Use some adequate approach to supervised learning. If the metrics results are good, you can start solving the task with unsupervised methods. Finally, speaking about embeddings-based recommended systems. In processing text, we have embeddings. The goal is to train some vector representation of words based on text that can later be used for further analysis. The point is, formulate an optimization task. What kind of conditions should the vectors conform to? For example, vectors with a similar context spread, words with a similar context spread, so words found in similar context, for instance, they should be close, meaning the scale multiplication is close. That's one of the ways of setting up the task. Of course, it has some kind of end formula. So solving this task with calculation and find the vectors. One of the classic examples is word2vec. It's been known for a while now, and it's been used in many fields. The main idea here is creating an optimization task so that the words found in similar contexts are actually close to each other. I mean, the vectors are. Now, there are two approaches here to building these vectors. One is try to learn to predict the context based on the word. So the word will give us a chance of finding something similar to it around it. Another one is knowing the context and finding the word. The optimization task is formulated pretty simply. Just formulate how do we use this multiplication, vector of the word and vector of the context? How do we get the chance that the word is found in this context? You can see the formula on the screen, and that's it. Obviously, why do I mention embeddings? The thing is, we can use it for formal languages too. For example, if we have user logs, we can interpret every action as a formal language word and build vectors for them or for their actions. We can also use these logs for goods viewed in the store and build embeddings for goods. Based on this approach, we can build a recommender system. We can check the user's sessions, the goods they viewed, generate a formal artificial text. You can just write out the identifiers for the goods they viewed and analyze that text. It's not that good though. It's better to use something else. Let's just write out the parameters of the goods they checked. If a person viewed orange sneakers, then red sneakers, we'll write that down. Orange trainers, Nike. Maroon trainers, Nike, etc. We'll analyze this artificial text with one of the embeddings models. Of course, we'll talk about the context size. We'll choose a context size that will have a whole number, because we have a fixed number of attributes for goods. And you can see the formula on the screen that you can use to get the vector of the session. Here's an example of how it can work on real data. This is an example from fashion retail. This is a user session example. They first checked a suit by Dolce & Gabbana, then some shoes, shows the brand here, the price logarithm, and the number of the category. And then we try to check the brand. We have a vector for the brand because it's one of the parameters. We can try to check what parameters are closest to that. And we get log price 11. So that's the price. Country is Italy. It is an Italian brand. People often check suits in that category. Also bow ties, etc. We can do the same in abstract categories. For instance, we can choose goods where the first word in the name is shoes. And we can also find out that there are so many categories, monks, derby, shoes, and others. There are also certain brands that are mostly viewed in this category. You can also make another query as a sum or a division or whatever. For example, let's take a suit and remove pants from it. What do we get? Tuxedos, jackets, and some other attributes that are characteristic for them. Now, if we use word2vec recommendations to just find goods with the vectors closest to the user session, the characteristic results show the following recall top 5 averages. It's compared to two-level approach. So the question is, why don't we use such recommendations, just word embeddings, as an alternative to our serious two-level supervised approach? Well, I call it unsupervised, but some people may say, well, in 2014, there was a paper that showed that it's not actually, that word2vec is actually implicit matrix factorization with a point-wise mutual information. So you can claim that word2vec is not exactly unsupervised, it's just another matrix factorization. And it's true, you can say that, another CF method. But we also consider the order of objects viewed. You can call it a supervised model, but something atypical. It's true about many unsupervised approaches. Well, it actually doesn't really matter if it's called unsupervised or supervised. What matters is that it doesn't optimize business metrics directly, but they demonstrate offline quality compared to supervised methods, and it shows that precision recommender systems can be built without direct optimization of business metrics, and it deserves some attention in the industry. Thank you so much. Ready for questions.